Welcome to a lesson with Dr. Powell. In this video, we'll look at a practice problem where we're thinking about types of discontinuities. In particular, we're going to be trying to decide which of the following have a removable discontinuity at x equals 1. And if it doesn't have it, we need to understand what it is instead. So we need to explain or show our work on each part, and then we'll identify which one is the removable discontinuity, but for each one we'll address the issue and say why not and what is actually happening there. So that's the question. And when you're ready to go for it, pause the video and try it on your own. On your mark, get set, pause the video. Okay, now here's the solution. We'll work through each one. Now on the first one, notice that it's nice and factorable. X minus 1, x plus 1, x minus 1. So actually, these cancel and you end up just getting x plus 1. Now, really, I mean, there's kind of an issue here because at least for part A and part B, I mean, x equals 1 is not even in the domain. X equals 1 is in the domain here. So really, for these two guys, they're actually continuous on their domain. The domain doesn't include x equals 1. So it's kind of nice. They are continuous. You could call them continuous functions if they're continuous on their domain. But for sake of this question and asking for discontinuity, well, something can't be continuous if it's not defined somewhere. If it doesn't exist, you can't say anything about it right there at that particular point. So yeah, I guess we'll call it a removable discontinuity there. Now why would it be removable in part A though? What have I just done? I just showed this function is algebraically equivalent to this one, which actually has its domain everywhere, including an x equals 1, which means that really this guy just had a hole and we just filled it, like taking a limit really. It's the same as a limit process. If you were to just now plug in 1, you'd get that limit, which would be 2. Hey, that's great. So really this is a hole here, and we saw that because of the algebraic equivalence between this and this with no hole. If it's algebraically equivalent to something without a hole, then and it's nice and connected, which this would just simply be like this, then that means the original not being defined there. I mean, basically it was just a hole right there. So which means it's removable. We can take the limit exists of this as x approaches 1 from both sides, and it will be the same thing. That y value will be right there. It could be filled in. So part A is the actual solution. This is the one that has a removable discontinuity. If you don't want to be too technical and say yes, discontinuities can happen off the domain. All non-domain points are discontinuities. All right, because it's not even continuous there. Great, whatever. Okay, but there is a way of redefining, or actually it was never defined in the first place right there, but defining the function right there at that point to make the y value fill the hole. So you can call this, say, sure, this one has a removable discontinuity x equals 1 in that particular, if we are thinking along those lines. Now, take a look at the next one. Again, it is going to be a domain issue, but so it doesn't have a discontinuity there. But if we were to take a look at this, when x is when x is think about negative. Think about 1. When x is a little bit bigger than 1, so think like 1 plus for x minus 1. What happens? Just kind of go on either side. So 1 plus minus 1, that's like 0 plus on the bottom. Here, yeah, okay, and maybe that doesn't quite, give it to us, because really what we need is the idea that we're going to get some cancellation here. Assuming that x is bigger than 1. If x is bigger than 1, then this up here, the top, is the same thing as just saying x minus 1, correct? If x is bigger than 1, then x minus 1 is positive, so it's going to be equal to its absolute value. Great. So when x is bigger than 1, those guys cancel to make 1, meaning that the function is, a constant 1 when x is bigger than 1. When x is less than 1, what happens? Well, the absolute value is not going to be, x minus 1 is going to be negative, right? To make it positive, you just put a negative in front of it, negative x minus 1. So this would be the absolute value of x minus 1, assuming that x minus 1 itself is negative. If this is negative, then putting a negative in front of it would make this equal to the absolute value of x minus 1. When does this happen? This happens precisely when x is less than 1. So in the situation when x is less than 1, the absolute value is just simply that on the top. Why did we do that? So we can see a cancellation. Cancel, cancel. We know this is going to end up being equal to negative 1. So when x is less than 1, the function's a constant negative 1. So it looks like negative 1 on one side, then positive 1 on the other side. The function right now looks like this with not being defined at 1. And is there any y value we can fill in that would make this continuous? No. This one wouldn't work. That one, none of them would work, right? So this one, that's y. A lot of people call this a jump discontinuity. Sure. A jump out of the domain discontinuity. Sure. All right. So then so that's why part B will not work. Part C now, it's defined everywhere. Great. But the graph of 1 over x minus 1, when x is not 1, well, 1 would be an asymptote for that, right? It's just the graph of 1 over x shifted to the right 1. So x equals 1, and, like this and like this. But then redefining what it is at 1 just be some kind of point like 2. Okay. Now, yeah, can I redefine it at 1? Anyway, so that you can never make that work, right? This is called an infinite jump discontinuity thing. So, nope. So the only one that really works is A. All right. And that concludes the explanation to that practice problem. Thanks for watching.